Okay, so I've updated this this today. I put in the I put in this morning's new case numbers. In this chart, we have like two halves to it. So there's the baseline data, which is let's see if this works now. Okay, good. All right. So we have the start of the current outbreak here. It goes up, and then we start at this point here where the vertical dotted line is where we start the baseline data. So I looked at all that baseline data between the two green lines, calculated the median of that data, drew the horizontal green control line, we call it, across there. So that's our baseline. That's what we're that's what we're looking at to determine whether there's a shift. Now, let me zoom in a little bit. Hopefully you can see that. So we're now not concerned about the baseline region. That's served its purpose for our current analysis. What we're concerned about is the data since the baseline. So we've got a series of points there. They sort of go up and down, and then at the end here, they seem to be. It looks a bit like there's a trend going up. So what we're looking for is firstly outliers. So when we're using run charts, we normally put in, well, we don't, this is actually a bit of an innovation, but we put in a horizontal line to mark where the outliers would fall. So this line that I've drawn there, that red dashed one, that is the upper fence from the canonical box plot. So that's 1.5 interquartile ranges above the third quartile. And in some situations you'd have a lower one as well, but it doesn't make, well, it could make sense under some situations to have a lower one here, but I haven't bothered with it, because what we're mainly just interested in is the cases going up. Now, outliers can mean various things. In a situation like this, a pandemic situation, we know, well, from fairly recent bitter experience in places like New South Wales, Sydney, we know that the underlying process that generates the data is a very volatile process, and it can escalate very quickly. So when you get an outlier, if you think you have a period of stability and things are under reasonable statistical control, and you then get an outlier, that's a real cause for concern. You'd be really worried about it. And and this doesn't just apply to pandemics. There are many kinds of situations where the underlying process is of a sort where an outlier is a real concern. So you find this in various chemical processes in chemical manufacturing, for example. The nature of the chemical process is that if it starts to get out of control, it just sort of escalates very rapidly, and next thing you know, you've got an explosion or something. So outliers are taken very, very seriously. Using the canonical box plot definition of an outlier, so a point that's beyond the upper fence or the lower fence, those outliers are going to be fairly rare with typical data. So with a typical sort of data with some random noise in it, you'd only expect, the probability of an outlier is about 1/6 of a percent. It's about 6 in 1,000 data points you could expect to be outliers. So in statistical process control, we normally use some sort of threshold like that. It's more common actually to set these outlier lines a little bit higher, so that it's maybe 3 in 1,000. But I think for a lot of practical purposes, just using the box plot upper fence makes sense, and it means you don't have to remember another calculation. So what we see in the post-baseline data here is we've got one point here that got very close to being an outlier, and then we've got a point up here which is an outlier. And so that you can be sure that you know, the medical health officials in Canberra were you know, got very agitated by that. But the thing is, they would have investigated, they investigate every case, but they would have known exactly what was going on there. My understanding is that what lies behind that outlier is not something that's trending across the whole population of Canberra. It's 2 or 3 infection sites. So there's an aged care facility which I think is attached to a hospital, and there are 2 or 3 construction sites, as far as I know. I think that's essentially what's driving most of this, what appears to be the start of a trend, you know, in this period here. But if we were just looking at this data and we wanted to decide, okay, it looks like things are going up. So if we go down to the next chart, this is exactly the same data. It's just I've put in the running median line. You've seen this before. So when you look at the running median line, it certainly looks like the start of a trend. Okay, the running median is smoothing the data. It's not overreacting. But you'd look at that. A lot of people would look at that and they'd think, oh gosh, it's starting to go up again, and they'd be worried about that. But the question, ideally, that you ask yourself if you have the right sort of data available is, well, is that statistically significant? Okay, or could it just be, you know, a bit of a random pattern? And that's the question that we can get an answer to using the shift test and the crossings test. So the outlier there is certainly cause for concern. We'd want to look at that carefully, but to determine whether there is a trend, a real trend there, we apply one of these other tests. Now what we're going to be looking for here is a run of 9 or more data points. I'll show you what we mean by a run. I did this last week, but I'll do it again because it's a little counterintuitive for some people. It takes a little bit of time to get the idea. Okay, so there's our data. So a run is 2 or more points on one side of the control line. So I'll mark some runs. So there's a run. That's a run of 2. And then we have another run of 2. Okay, that's above. So they've got a run below, a run above. That's just 1 point, so that's not a run. That's 1 point. That's not a run. Then we go below the line here, and now we have a run of 3. Then we bounce up above the line. That's just 1 point. Then we go below the line, and again we've got a run of 2 there. Then we shoot up above the line again, just 1 point. Down below the line again, just 1 point. Above the line again, just 1 point. Below the line again, just 1 point. And then things start to get interesting. So let's focus in a bit on what's happening here. So we have a point there which is on the control line. It's on the median line. For this test, we just ignore that. Okay, it doesn't count. So then we have 1 point that is above the line, and then we have another median point which we just ignore, and then we have another point which is above the line. So the way we actually process this in our minds is we say, okay, that's part of a run and that's part of a run. So we've got, so far there, we've got 2 points in a run. Okay, we're ignoring that this hasn't crossed the line. We just ignore those 2 points on the median. Then we've got another point above the line there. So now we've got 3 points in our run, and then we've got another one which is 4, and then we've got 5. So that's a run of 5 points there, with 2 points on the control line that are ignored. Now that's the bit that confuses people, is what you do about the points that are on the line. If I could put it to you another way, I'll just get rid of that. It's as though we just sort of pretend those two are not there, and it's as though the line here just went like that. And so what we'd say 1, 2, 3, 4, 5, and that would be the length of our run. So we have a run of 5 there, but we actually need a run of 9 to be able to say that we're 95% confidence there's a shift in the median. And I'll explain to you in a moment where that 9 comes from. But that's what we're looking for. So that's the run test. The other test we do is called the crossing test. So let me just get ourselves back down again. Okay, so that's the run test. We get these numbers from a table, basically. I put a little extract from the table somewhere down here. Okay, so you'll see for however many data points it was, 23 I think, the upper limit for runs is, realise that, says the upper limit for runs is 8. So what that means is we can't claim a significant shift until we see more than a run that is bigger than 8. And the other column here is, this is the crossing. So the crossings test would be we would want to see that there are less than 7 crossings, so 6 or fewer crossings. We'll just go back and investigate the crossings. Okay. All right. So, oops, that's the wrong one. Okay. So when we do the crossings, we still have the same thing about ignoring the ones that are on the median line. Okay, so all right. Okay, so let's look at the crossing. So we don't count that first crossing there because that's we haven't even hit the first data point there. So we've got, I'm just going to mark the actual crossing. So there's 1, and then we've got, it goes down under the line and back up, so we've got 2 there. So that's 3 crossings. Then it goes up and down 4 crossings, up and down 5 and 6. Okay, and then up and down 7, 8, and then we've got 2 more, 9, 10. Now, we have, what happens here is that counts as a crossing there because the line is going from below the control line and up again, but that one there, that doesn't count as a crossing. Okay, we just kind of treat that as it bounced off the control line, it didn't cross it. Okay, so that doesn't count as a crossing. So we need to find 6 or fewer crossings to be able to claim a statistically significant shift. And we've actually got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we're not even close. So what will have to happen, I mean, we certainly don't want to, in the next week, find a statistically significant shift upwards if we can at all avoid it. But for that to happen, we would still need a few. This trend above the control line would have to continue for a few more days. So fingers crossed, we'll see what happens during the course of this week. So that's my first example of how this works. Now, the beauty of this technique is, of course, that it doesn't require you to do any calculations, and it doesn't really require a great deal of explanation. It's a technique, although this kind of technique is quite old. It was invented back in the 1930s, but this particular version of it with the shift and the crossings test only goes back, I think, I can't remember when the earliest paper was, but it was only about 8 or 10 years ago, and it was developed in a hospital administration setting. So the people who developed it and the people who use it are very well educated about these kind of statistical things, and they certainly would want to make sure that it actually did what it claimed to do. But the beauty of it is that you can use this for all kinds of things. I once helped a friend lose weight using this. The friend kept a run chart like this of daily weight measurements, and didn't make a claim to have lost or gained weight until the run test or the crossings test actually stated that they had. And that actually worked quite well, because when people try to lose weight, there's typically this sort of random up and down noise, which for an average sized adult can easily be, 1 or 2 kilograms over the course of a week. So it's very hard to tell, whether you're really losing weight over the course of shortish time periods. And people get very emotionally involved in this, and they get angry that their exercise regime or whatever isn't working, and so on. Whereas if you use something like this, it kind of imposes a discipline, and it's constantly reminding you that you can't really make a call about whether you've achieved a weight loss or a weight gain unless you have, at least about 10 days of data behind you. So it worked quite well for that. I mean, it's a case of one, but it was an interesting application of it. But it's used a lot for quality control things. For it's used in environments like, say, hotels, for keeping measuring failures in service provision, or things taking too long, or complaints, and so on. And the beauty of it is that you can have it stuck on a wall somewhere in the office or in the factory, or in the hospital tea room or whatever, and everyone can see it, and pretty quickly everyone learns how to read it and what it means, and nobody has to know how to do any calculations to use it. Okay, so let's just dig in a little bit more into this. Just clean up my text here. So I don't know what that mystery yellow square is there. Anyway, I'm stuck with it. All right. So this is an example from one of the papers by the people who developed this technique. And it's an example from a hospital, which I think was a hospital in Europe somewhere, where what they wanted to do was an experiment. So it's what we call an interrupted time series experiment, or a before-after experiment. And these are very useful experiments. We do them all the time. Well, they are often done in business contexts. They should be done more, probably. So what they were concerned about was the rate of mortality, so people dying after they'd had operations. And the experiment they tried was they introduced into the hospital, into the operating theatres, a pretty simple looking tool. So it's this thing. It's this thing here, which is the World Health Organization surgical safety list. So this, when you look at this thing, I mean, you look at it and you think, do they really have to be told to do this? You know, you know, before you put the person under the anaesthetic, put them to sleep, have you confirmed their identity? Have you confirmed where you're going to operate? You know, is it the left lung or the right lung? What is the procedure? And have they given their consent? And then, has the site for the operation been marked? Have they done the anaesthetic machine and medication check? Is the pulse oximeter, that's the thing that goes on your finger and measures the oxygen content of your blood, is that switched on and working? Check for allergies and so on. This kind of sounds like fairly obvious stuff, but in a hospital environment, what actually happens is there might be several different people that are responsible for these things, and they typically are operating under a lot of time pressure and so on. And so it's, you know, there's always a risk that these things will go wrong. And then there's a few other things before you actually make a cut, a skin incision. You do things like make sure everyone in the operating team has introduced themselves by their name and people know what everyone's job is. Confirm the patient's name, various other things here. And then before the patient leaves the operating room, there's a few other things that are done. You count everything to make sure that nothing's been left inside the patient, for example, and so on. Now, it seems like a pretty simple checklist. What happened, let's show you the full chart now. So this is the full chart. I think everyone can see that. Okay, so I've just copied and pasted this out of the paper. So if you want to look at the paper, I've actually put it up on Wattle, and there's a DOI reference down the bottom there. So you can see there, that's the baseline marker. So there's 2 years, there's 24 months of baseline data. So they didn't wait 2 years to introduce the checklist. They had historical data for 2 years. So they introduced it, as far as I can tell here, on the beginning of January 2012. And, you know, you could just eyeball that and immediately see, boy, something changed. Although you've got to be aware of the scale here. So the change here, the control line, the median control line, is at 1.1% of the patients dying, and the median of the post-baseline data is 0.7%. What am I talking about? Yes, that is the median. Yeah. So, but if we use the, if we look at the runs test and the crossing test, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 months of data there. So if we look at our little table, which I should have down here somewhere. Okay, we go down, we look at 11. So for the upper limit for runs is 6, so we're looking for a run of 7, and the lower limit for crossings is 2. So that means we would only, the crossings test would have to see only 1 crossing. So let's go back and have a look. Start with the runs test. So we have a run, so the run starts there. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 all below the control line. Okay, so that just by itself, that is you know, quite strong evidence that we should be 95% confident that there's been a downward shift in the median number of post-operative deaths. Now, the crossing test, however, we might need to zoom in for the crossing test, although it's kind of obvious that it doesn't pass the crossing test because you've got 2 crossings there, 1, 2, and we would only need, it would have to be less than 2, in other words 0 or 1, to trigger the crossings test. So that's so the situation there is past the runs test, or I keep calling it the runs test, so it's interchangeably known as the runs test and the shift test. In this paper they call it the shift test. I'm pretty sure in an earlier paper they call it the runs test. And historically, going back to the 1930s, tests like this, not exactly the same as this one, but tests that used runs were called runs tests. These guys have called it the shift test, but it's the same thing. So we're looking for runs. We've got a run of 9. We only needed a run of, what was it, 7. So that's a pretty clear story. But the question you might ask is, well, what does it mean if it passes the runs test and it doesn't pass the crossings test? Is that some kind of contradiction? And the answer to that is no, it's not a contradiction. So you only need one of them. Sometimes you'll get the runs and not the crossings. Sometimes you'll get the crossings and not the runs. Sometimes you'll get both together. And sometimes, of course, you'll get neither of them. And that's where I think it should be left. The authors of this paper have gone on with others to do some other work to try and see whether there's some way you can, get even stronger results by considering the runs tests and the crossings tests together. And they've kind of come up with a method, but it's rather complicated, and I think you pretty much need software for it, and it actually it detracts really from the attraction of this method, which is you don't need software, you don't need to do any kind of calculations, you just work with the visualization. So I wouldn't worry about that, but just remember that you only need to get a signal. That's the way we think about it, is you get a shift test, correct myself, a shift test signal and or a crossings test signal. So you get one of them, you're good. You've got the 95% confidence. Okay, now I just want to clarify some things about statistical control. This is a huge subject, so you can do whole degrees in statistical control. There's professional qualifications in it. It's usually called, it's branded as Six Sigma. It's often called total quality management. They're the same thing, basically. It was invented in the United States back in 1935. It was used during the Second World War, and then the Americans forgot about it for a long time, except for one guy who took it to Japan, and in Japan they really developed it and made it a huge thing. And then when the American industry was suffering from competition from Japan, eventually, I think it was Motorola was the company in America that originally developed the Six Sigma thing. They sort of rebranded it and built in all this stuff about black belts and yellow belts and green belts and whatever, and that's become a huge thing now. So, there's lots of people get Six Sigma qualifications, but it's actually the same old statistical process control that was invented back in the 1930s. So, but it's a really important idea. So the basic idea here is, let's use this as an example. You want to improve something. You want to improve a process. So it's always about a process. It's always about something that happens over time. You want to improve a process. There's variation in the process. It goes up and down. There can be two causes for variation in the process. So the way to think of it is, one kind of variation can just be intrinsic to the process itself. The process naturally produces a certain number of errors or failures or whatever. And then you can also have what are sometimes called special causes. So they can be things that make the process worse at certain times, typically. So the classic example that everyone jokes about here is that you never buy a car that was made on a Monday, because the factory workers spend their weekend drinking and partying, and then come to work on Monday with hangovers, and any car that's made on a hangover is made on a Monday, sorry, is going to be, you know, it's going to be a lemon. It's going to have things wrong with it. Now, I don't think that's much of an issue these days. Might have been once, but that's the classic idea. So what it means there is that you'd have a car manufacturing process that had a common cause of things, defects in cars, which would occur on any day of the week, and then you would get these sort of blips on Mondays of extra defects that came about because the factory workers all had headaches and, you know, couldn't see straight. So the idea, the central idea of statistical process control is you identify those special causes first and get them under control, get them fixed, and then you have a process that's under statistical control. It may not meet your requirements, it may not be good enough, you may want to improve it, but at least you know that when you try an experiment like this intervention with the World Health Organization checklist, you know that when you see a result, the result is due to your intervention and not to some special cause that's going on. That's really the central idea. So the thing to do is to you know, try and get clear about whether you have a stable, statistically controlled process on the basis of which you can set your baseline. And that part of it is usually done by taking into consideration outliers. So if your process, what you're hoping to be your baseline process, keeps throwing up outliers, that suggests that there's something badly wrong with it. Or, you know, what you could have done in this situation probably is calculate, you know, maybe they did this, I don't know, calculate a baseline there and then see whether the second half has any significant runs or you know, crossings or whatever where you'd say there was a trend. If there's no trend there, then you say, okay, well, that's suitable to use as a baseline. And then you get your baseline right, and then you can do your intervention, which happened here, and then assess the result. So that's really what it's all about, but it's an extremely powerful and useful technique. And although its main applications historically have been in manufacturing, it has much wider applicability than that, and it actually should be used probably quite a lot more than it really is. I think one of the problems is that, you know, if you go and do a course on this, you do get thrown into quite a lot of mathematics and calculations and special terminology and so on. So the way I see it is there's a lot you can do with just the run chart. Okay, with these new tests, the shift test and the crossings test, that will serve for a lot of purposes. If you do a course in statistical process control, you go and do a Six Sigma course or a TQM course or something, you'll learn about a whole series of different charts. They call them generically, they call them control charts, and they're used for different specialized applications. But those courses, you know, there's quite a lot to learn. And a lot of people wouldn't have the time or the interest, or, you know, they might be put off by the mathematics or whatever that's associated with it. But for a lot of just straightforward everyday applications in business and organizations, just this simple, relatively simple run chart with these the shift and crossings test, I think is just a really useful little tool. Okay. Starting next week, we're going to be talking more about experiments, so I'll probably, you know, mention this again. But that's the main idea. Okay, it's all covered. Now, I've given you, I think, pretty sure on Wattle. Where did I put it? Where are we? Development. Okay. Okay, yes. On Wattle, I've put a full table of these. Sorry. This is the full table of the threshold limits for the shift test and the crossings test. going right up. So starting at, so 10 is basically the minimum number of baseline measurements you'd want to use, and this goes up to, what is it, 98, I think. So what else can I say about it? I think, did I put the formulas there? No, I didn't. Okay. I usually get a question along the lines of, how do you calculate those shift and runs numbers? And the answer is in that paper that this was taken from, and I've put that paper on Wattle, so you can read all about the mathematics that lies behind this, and they did a bunch of simulation studies and so on to test all of this. Okay, that's run tests. Any questions on that before I move on to the next thing? Good. Okay. All right. Oh, I got another example. Okay, let's do the other example. This is New South Wales COVID cases. So you can have a look at this, because everyone in Australia, there's a whole lot of talk in the news and so on at the moment about how New South Wales is supposedly coming out of the pandemic, and the tide has turned and so on. And so what I did was I just got I've got 30 days of data there. So the baseline I've used starts on the I forget when it starts. It goes up to the 10th of September anyway. So that's the baseline there. And those two peaks there, they are actually the two highest numbers of daily cases in the, I think it's actually in the whole time in Sydney, but certainly in the current Delta variant outbreak. And so I've set a baseline there, and then what we need is a run of more than 7 data points to identify a statistically significant shift. So when you look at that, we've got 1, 2, 3, 4, 5, 6, 7, 8. So we've got a run of 8 there. So that just sort of barely meets the test. And if we look at, did I have the crossings? We need less than 4 crossings. Let me zoom. The crossings are a bit interesting in this one, so let's have a look at them. Okay, so we don't count that first one because that's coming off the baseline. So we've got a run there of 1, 2, 3, 4. Then we have a crossing. And then, now this is, the reason I'm saying this is interesting is just that we've got a data point there which is, it's just barely below the control line. And I'd probably give that the benefit of the doubt and say it's on the control line, near enough, and I wouldn't count it as a crossing. So in that case, the next crossing is not until here. So there's a crossing there. So we've got 2, and that's it. Now, and what did I say we needed? We need less than 4. Well, we've got less than 4. So that case, that passes the runs test and the crossing test. Now, the qualification I keep making about this sort of COVID data is that pandemics are an unusually volatile kind of data generating process, and I would be very cautious and qualified by saying there is a downward trend there, but it certainly looks like it. And I think in the case of New South Wales, because the numbers are so large, there's probably a bit less of the kind of local effect that we get in Canberra. So I mentioned that I think a key thing driving what looks like an upward trend in Canberra is probably only about 3 locations where, you know, there have been 10 or so cases from one contact location or workplace, basically. That has kind of skewed things. It's not an across the population effect. So I'd be a little cautious about that, but certainly it looks like that. The medical experts that are making judgments about New South Wales and shifting down the some of the health measures and so on, they have a lot more information to work with than we would have in the chart like this. So I'm sure they're looking at lots of other things, and particularly the reproduction rates and vaccination rates and so on. Okay, but we can, on the strength of it, we can say, well, in the absence of any other information, we can be 95% confident that there's been a downward shift since the baseline period. I should mention what you do in practice when you're tracking a process is once you're really sure there's a downward shift or an upward shift, then you set a new baseline. And then you monitor what happens after that.